Hey guys, welcome back to the CS Classroom. In this next video, we're going to cover topic 2 or subtopic 2 in topic 1 for paper 1. And this is called data representation computer logic. So let's get started. We're going to focus mainly on binary and representing binary values in different ways. And then we're going to talk about logic, logic gates, truth tables, and logic diagrams. So the first topic we're going to talk about is going to be binary. And basically, we'll get more in depth as to what binary actually is, but when we're talking about binary values, we're talking about a system of representing values by either a 1 or a 0. So really, when we're representing values in binary, we have two options. We have a 1 or 0. And in the context of computers and electronics, a 1 can represent on, and a 0 can represent off, or a 1 can represent true, and a 0 can represent false. So a binary value may look something like this. And what this essentially is a series of electrical signals. And those electrical signals can be perceived or viewed as something as like on, off, on, off, on, off. Basically a series of on-off signals. And the more bits we have, the more complex this series of signals is, which eventually allows us to represent things in a computer like colors, and computer code, and even going up to the level of allowing us to execute very complex pieces of software like games, or even something like Microsoft Word, which I suppose it's not that complex, but still, it's, if you think about just representing a whole computer program using just ones or zeros, it is actually pretty complex. And one thing I do want to clarify before we move on is how units work in terms of storing data. So if you look back at our previous slide, I did show you guys that, for example, 1024 bits is 1 kilobyte, 1 megabyte is 1024 kilobytes, etc. And this is essentially the kind of measurement of units that's used if you're going to go buy something at the store. But if we're really looking into computer science, if we are looking at storage sizes in terms of 1024, so by that we mean powers of 2, then we're actually referring to them as kilobytes, megabytes, gigabytes, terabytes, etc. Okay? So again, in the store, they might be sort of referred to as this, but technically, that's what we're really talking about. So for example, if we just have 1024 bytes, like right here, that's going to be a kilobyte. And then 1024 kilobytes is going to be a megabyte. And 1024 megabytes is going to be a gigabyte, and so forth. Now, if we're talking about data in terms, if we're talking about data in base 10 terms, so we're talking about multiples of 1,000 bytes, then we're really talking about kilobytes, megabytes, gigabytes, etc. So remember that multiples of 10 are traditional measurement values, and multiples of 1024, that's going to be ones maybe you're not familiar with, but they're still referred to in the store as kilobytes, megabytes, and gigabytes. But the difference is worth knowing because we're getting into like sort of formal computer science, right? We're not going to go buy something at the store on this exam. So I just wanted to clarify that. Let's move on. Now, if you think about file sizes, generally, if we're just talking about a character in a text file, that's going to be 1 byte. It depends on the system that's used to represent those characters, but that's just a good ballpark estimate. An email might be 2 kilobytes. A large photo or high resolution photo might be 11.4 megabytes, and a 1 hour video might be 4 gigabytes. So let's take a deep dive into what binary actually means. So binary can be used to represent all types of data on a computer, and binary is essentially the language that a computer speaks. So when a processor is going to execute instructions, it executes those instructions as ones and zeros. The CPU is going to use binary to perform calculations and logical operations. So it's not only the language that is accepted by the processor, but it's also what's used to actually perform operations. And this is partly because binary can be used to distinguish between an on or off state. So really, like binary code, as we said before, is just a very complex series of on and offs. Okay, so now let's talk about how binary actually works from a mathematical perspective and then apply it to the type of problem that might appear on the IB exam. So first off, before we talk about binary itself, I want to talk about the numbers we're used to using, and those are Denary numbers. So these are numbers like, for example, 5,427 that we would see in everyday life. Now, 5,427 looks pretty simple, but the reason we actually call it a Denary value is because it's written in what's called base 10 form. Base 10, which uses a term that you may have seen associated with exponents. And let's see why that's the case. let's say we have 5,427. Starting from the right to the left, how this number is actually represented, or what it's actually representing, is essentially powers of 10. So if this is 10 to the power 0, this is 10 to the power 1, 10 to the power of 2, and 10 to the power of 3, then we can use these to actually calculate its value. It's kind of redundant because it's going to give us 5,427. But basically what happens is we can multiply 5 times 10 to the third, which is going to give us 5,000. And we can add that to 4 times 10 to the second, which is going to give us 400. We can add that to 2 times 10 to the first, which is going to give us 20. And then we can add that to 7 times 10 to the power 0, which is just going to give us 7, and we get 5,427. Now, like I said, we still end up with our original answer, 5,427, but you can kind of see the function that 10 as a base plays when we're dealing with these types of numbers. So if these numbers we're used to are written in base 10 notation, right, where essentially each digit is some multiple of 10, right, so some 10 to some exponent, then we can go ahead and we can see how binary works, because binary is base 2 notation. So what that means is that let's say we have a binary value. Let's say we have a binary value like 1, 1, 0, 1. Now, this is base 10. So base 2 is going to look something like this. The first digit right here, starting from the right, is going to represent 2 to the power of 0. This is going to represent 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So how we can convert this to a Denary value is by doing the same process as we did above. 1 times 2 to the power of 3 is going to give us 8. 1 times 2 to the power of 2 is going to give us 4. 0 times 2 to the power of 1 is just going to give us 0. And 1 times 2 to the power of 0 is going to give us 1. So that means this binary value right here is just equal to 13. So we have base 10 and base 2, and you can kind of see the relevance of having these bases and how they represent different digits in a given number, given the form of that number, given the base of that number. Now later on, we will look at hexadecimal, which is actually base 16, but it'll work according to the same principle. So now that we've seen this, let's go ahead and let's look at the first type of problem that you'd have to solve, which is converting binary values to Denary values. So we have the binary value. So the way we can do this, first, the easiest way is to start by writing out the different exponent values, or the different exponents of base 2. So as we did in our previous example, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. And what I'm going to do as well is I'm going to go ahead and write out these values are as whole numbers just to make things easier. So 2 to the power of 0 is 1. Now you get the idea. Okay. Now if you want to calculate the Denary value of this binary value right here, we're basically going to go through the same process as we did before. So first we're going to start on this side essentially, right? And we're going to see what each one of these values represents. So the first one is going to represent 1 times 2 to the 7th. And that's going to be 128. And next we have 1 times 2 to the 6th. So actually this should be 2 to the 6th right there. And that's going to represent 64. So we have 1 times 2 to the 6th. So we can add 64. Next we have 2 to the 5th. So we can do 1 times 2 to the 5th, which is going to be 32. And next we have 0 times 2 to the 4th, which is just going to be 0. So we're actually going to skip that. And next we have 1 times 2 to the 3rd, which is going to be 8. And we have 0 right here, so we're going to skip that. And we have 0 right here, so we're going to skip that. And then we can go ahead and do 1 times 2 to the power of 0, which is just going to be 1. So if we add all of these values up, then we just end up with 233. So maybe that was a bit confusing, so let's go ahead and let's do a few other examples. So next we have our binary value. We have 1. Now I'll go ahead and write out the exponents, and we can go ahead and we can see which one of these values, or which one of these exponents correspond to a 1 in the actual binary value and which one don't. So right here we have a 1, right here we have a 1, right here we have a 1, and right here we have the 1. So those are the only ones that we really care about. So let's go ahead and let's write those values out. We have 128. 1 times 2 to the power of 7 is 128, plus 8, plus 4, plus 1, and that's going to give us 141. Now, let's just do one more example. Okay, so now we can look at where we have 1s, and we can write out our values. So this is going to be 512 plus 256, and we don't care about the 0, so we're going to do plus 64 plus 4 plus 2 plus 1. And that's going to give us 839. So now that we've learned how to convert from binary to denary, let's go ahead and let's convert from denary to binary. Now, the trick to this is to figure out the biggest binary value that can fit into our denary value. So if our denary value is 168, let's go ahead and write out our powers of 2. Now we're going to stop at 2 to the power 7 because most values that we're going to be working with are going to be 8-bit values. They're going to have 8 binary digits. So 2 to the power of 7, it represents 128. But if we go to 2 to the power of 8, that represents 256. And 256 is too big to fit into 168. But 128 fits into 168. So right here, we're going to put a 1. Like I said, we're going to start with the biggest binary value that can fit into our denary value. And that is 2 to the power of 7, or 128. So we're putting a 1 there. And next, we're going to do 168 minus 128. We basically accounted for 128 out of 168 right up here. So now we have 40 left, and we need to account for that in the rest of our binary digit. Now, 2 to the power of 6 is going to be 64. And 64 is actually too big to fit into 40. So we're going to put a 0 right there. 2 to the 5th is going to be 32. And 32 does actually, oh, sorry, my bad. We're going to put a 0 right here. As I said, that should be 0 because 64 doesn't fit into 40, but 32 does fit into 40. So we can go ahead and we can put a 1 right there, and we can continue with our arithmetic. And we can do 40 minus 32 equals 8. So now we still only need to account for 8, and we'll keep moving on. So 2 to the 4th is 16, and 16 is too big for 8, so we can go ahead and put a 0 right there. 2 to the power of 3, however, is 8, and that's perfect, so we can put a 1 there. But 8 minus 8 equals 0, so we have nothing more to account for. So that means that the rest of the values are going to be 0. So this right here is going to be our answer. So let's go ahead and let's do another example. So now we have the denary value 83. Now if we're looking at our powers of 2, 128 does not fit into 83. 128 is too big, so we can go ahead and just put a 0 right here. But 64 does fit into 83, so we can go ahead and put a 1 right here. So if we do 83 minus 64, we end up with 19. And so that means that we still need to account for 19. So now we're going to go to 2 to the power of 5, or 32, and that's too big, so we're going to put a 0 right there. And now then we're going to go to 16, and 16 does fit into 19. So we can go ahead and we can do 19 minus 16, and put a 1 right there, and we have 3 left to account for. But 8 is too big for 3, so we're going to put a 0 right there. 2 to the power of 2 is 4, and 4 is too big for 3, so we're going to put a 0 right there. 2 to the power of 1 does fit into 3, so we can put a 1 right there. And that's just going to be 2, obviously. And then so we can do 3 minus 2 equals 1, and we still have 1 to account for, which can be 2 to the power of 0. And so this is going to be our binary value. Now what's important to note is that this binary value, this is an 8-bit value. 8 bits. That's what that means. Now, you might be asked to represent these values in different numbers of bits. So this is the 8-bit representation of 83. Now let's say that the question or the exam wanted you to give a 12-bit representation of 83. All we would do is we would just add 4 zeros, right? Now we have 12 bits, but the value hasn't changed at all because those are all zeros. So that's just something to keep in mind. Okay, so now the next type of number form that we need to learn about is hexadecimal. And while denary was base 10 and binary was base 2, hexadecimal is base 16. And hexadecimal is used to more efficiently represent large binary values. And that's because each binary value each hexadecimal digit is worth 4 binary values, right? So think about it. Hexadecimal is base 16, binary is base 2, 2 to the power of 4 equals 16. So for example, if we have a particular set of binary values like this, it can be represented by 1 hexadecimal digit. And we'll look more at that in the next few slides. Now, hexadecimal can be used to efficiently represent colors, memory addresses, as we saw earlier, MAC addresses. And MAC addresses are used to identify network devices on networks, and these are addresses that are stamped into each network device during manufacturing. So let's take a look at how hexadecimal works in relation to denary, and later we can move on to binary after that. So let's say we have a hexadecimal value. So right here we have 2A5, right? Now we're going to look at this the same way as we did with binary. So the first digit is going to be 16 to the power of 0, then 16 to the power of 1, and then 16 to the power of 2. And we can multiply right here. We can multiply 2 times 16 to the power 2, or 2 times 256, which gives us 512. And then we have 16 times 10, which equals 160. And A actually represents 10. And the reason we actually have an A here is interesting. So remember, for binary is base 2, and then we have 1 and 0. Base 10, we have the numbers 0 through 9, right? So you have 10 digits. Accordingly, for base 16, we have 16 digits. And 10 is going to be A, 11 is going to be B, 12 is going to be C, 13 is going to be D, E is going to be 14, and F is going to be 15. So A just means 10. So in this case, we'd multiply 16 times to the power of 1 times 10, which equals 160. And then we'd have right here, we just have 16 times 0 times 5 equals 5. We'd add those up to get 677. So 2A5 in base 16 is going to be 677 in base 10. Let's take a look at another example just to kind of make things clear. So let's say we have the hexadecimal value. We have B, D, and I'll go ahead and space these out a little bit more so we have some room to work with them. So we have B, D, and E. Now B, remember, according to hexadecimal, is going to be worth 11, and this digit right here represents 16 to the power of 2. 16 to the power of 2, 16 to the power of 1, and 16 to the power of 0. So right here, we're going to have 11 times 256 plus D, remember, is 13. So 13 times 16 to the power of 1, which is 16, plus E is 14. So 14 times 16 to the power of 0, or 1. So these are the values we get after doing the multiplication, and our answer is going to be... Now, if we decided to add another hexadecimal digit, so let's say we had like, I don't know, we had like F right here. That would make things significantly complicated because this digit is going to be representing 16 to the power of 3, which is like 4096. So let's not go there, and we're probably not going to see that on the IB exam. So let's go ahead and do some basic examples that involve converting to hexadecimal, from hexadecimal to denary, like we just saw in the previous slide, but this is just for some additional practice. So let's say we have 3b, okay? So 16 to the power of 0 and 16 to the power of 1. So to get our answer, we're just going to do 3 times 16 plus, remember, b is going to be 11 because a is 10. And we're going to be ending at 15, so f is 15. But anyways, b is 11. So we're going to do 11 times 16, or 11 times 1, right, which is just 11. So we have 48 plus 11, which equals 59. Now next we have 18e. So let's take a look at that one. This one's a little bit bigger. So here we're going to have 1 times 256 plus 8 times 16 plus, remember, e is going to be 14 because the last digit in hexadecimal represents 15, which is f. So we're going to have 15 times 1. So 256 plus 48 plus 15. And actually, my bad, this one isn't 48, is it? So actually 8 times 16 should be 128. So our final answer is going to be 398. And that's essentially how you can convert from hexadecimal to denary. Now let's say we want to convert from denary to hexadecimal. So there's a few ways to do this. For me personally, I think the easiest way is the same way as we did our base 2 conversions, our binary conversions. So let's say we have the value 495, right? So you have 16 to the power of 1, or we have 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. This is equal to 256. So 16 to the power of 2 is equal to 256, and we know that only fits into 495 once. So we can go ahead and we can put a 1 right there. So if we do 495 minus 256, then we get 239. And next we want to see like how many times. So right here we have 16 to the power of 1. And we can go up until f. So f would just be like 15 times 16. And that equals 240, which is more than the 239 we have left. But actually at the same time, it's not that far away. So really our answer is probably going to be 14, right? So 14 times 16 equals 224, and that fits into 240. And 14 in hex is just going to be, remember, it's going to be e. So then we can do 239 minus 224, which is going to be equal to 15. And right here, if we want to represent 15, we can just use F. And so our answer is really just going to be 1EF for what that is in hex. So basically the same logic as we did for binary, just a little bit different because we have more values than 1 and 0 to work with. But just to make sure you get it, let's look at some other examples. So let's say we want to convert 480. So let's write out our values. Remember, 16 to the power of 2 is 256. So if we do 2 times 16 to the power of 2, then that's going to give us 512, which is still too much. So this is probably just going to be a 1 right here, right? So that means that we're going to have 256. But if we do 480 minus 256, then we end up with like 224. And so we have 16 to the power of 1 right here. So we need to figure out how many times we can multiply by 16 to get 224. And if you actually remember from our last question, that's just going to be 14. 14 times 16 equals 224. And 14 is represented by E, so we're just going to put E right here. So now we actually have nothing left because we fully accounted for 224 right here. So all we need to do right here is just put a 0. So now let's take a look at another example, our last example. So now we have 232, and we want to represent this in hexadecimal. And we only know we need 2 digits because if we have 3 digits, that's just going to be, we're going to have a minimum of 256, right? So we have 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. And this is 256, but 256 is already bigger than 232. So this is just going to be a 0. Because if we had a 1 right here, then we would have at least 256. So now we need to figure out how many times 16 to the power of 1 can fit into 232. And if you remember from our previous problem, we already know that, 16 times 14 equals 224. And 16 times 15 is going to be equal to 240. 240 is bigger than 232, so we can say this is going to be 14, or E. So if we put E right there, then that means that we've accounted for 224 out of 232. And 232 minus 224 is equal to 8. So that means for our next digit, we're just going to put an 8 because that's going to give us 8, right? So our answer is just going to be E8. Anyways, that's how you convert from denary to hexadecimal. Let's move on. Okay, so now let's talk about the relationship between hexadecimal and binary. So we know that each hexadecimal digit represents 4 binary bits. So let's see how that actually works in practice. And this is going to kind of include denary calculations. So let's say that we have this particular value right here. So we have 1, 1, 1, 0, 1, 1. We have a 6-bit value, but just to make it 8 bits, we're going to add an extra 2 zeros. Because remember, if each hexadecimal digit represents 4 binary bits, that means that this should represent 1 hexadecimal digit, and so should this. So what we're going to do first is each of these groups of 4 bits, we're going to convert into denary. And that just kind of makes it a bit easier to eventually convert to hex. So we'll just go ahead and write out our exponents because maybe you don't have this fully down yet. So based on these exponents, this is going to be 8 plus 2 plus 1. So that's going to be equal to 11. Do the same thing right here. Actually, we don't care about those. So this is going to be equal to 3. So you have 3 for first bit, our first group of 4 bits, and 11 for our next group. But 11 can only be represented in hexadecimal as B. So our answer is going to be 3B. Now let's take a look at our next binary value. So this is our next binary value. And again, we're going to split this up into a group, right? So what this is going to give us right here is we have 2 plus 4. So this is going to be 6. And this is going to be 1 plus 4 is 5 plus 8 is going to be 13. So if we turn this into binary values, remember 13 is represented as D in binary. So our final answer is going to be D6. Now last, we're going to look at an example of going the other way around, right? So how can we represent this as binary? So basically what we can do first is we just need to see what denary values these are. It's just easier to go from hex to denary first. This is going to be 10, this is going to be 3, and this is going to be 15. So the way we represent 10 in binary is going to be 0, 2, 0. That's going to give us 10. 3 is just going to be 0, 0, 1, 1. And 15 is going to be 1, 1, 1, 1. So you've got 8, so it's 12, plus 2 is 14, plus 1 is 15. So this would be F3A would be equal to this right here. Okay, so now let's take a look at a practice question. And we're only going to take a look at one practice question here, but remember, if you join the members program, then for each one of these videos, I have a set of practice questions you can access and go through. And this is constantly being updated. And as soon as the first exam comes out, this will be updated even more often because we'll have more to work with. Anyways, first, state why hexadecimal numbers are frequently used in computing. So the main reason is because they're a more compact way to represent binary values, which are sort of the main way of communicating logic, mathematical operations, and values in computing. There's a more compact way. Next, state the number of bits used to represent a non-primary color, such as yellow, or I guess like purple or something like that. Now to figure this out, let's go ahead and read the question. So it says colors are represented by a computer as a combination of 3 primary colors, red, green, and blue. Numerical values are used to represent the different shades of each primary color. These values range from 0 to 255 in decimal, or 00 to FF in hexadecimal. So basically what this means is that we're representing 3 colors. For every shade or every color that we have, this is going to be a combination of some shade of these 3 colors, okay? And each one of these primary colors is represented by something like this. So 0 to FF in decimal. Now, if we're looking at 0 to FF in decimal, right, then we're essentially looking at that's 4 bits and that's 4 bits. So essentially, each one of these colors is being represented by 8 bits, each one of these primary colors. Also 0 to 255, that's going to be represented by an 8-bit value at maximum. So if each primary color is 8 bits and we're representing any given color by a combination of the 3 primary colors, that means that the number of bits used to represent a non-primary color, such as yellow, would be 24 bits. State the maximum number of colors that can be represented in a computer pixel. So we're going to talk a little bit further along about how colors are represented and what pixels are. But essentially each pixel is a little square on a computer screen. And the color in that square is represented by a 1 or a 0. Sorry, it's not represented by a 1 or a 0, but it's going to be represented by a single 24-bit value. So 24 ones and zeros. Now, if we have 24 ones and zeros, and every combination can be used to represent a color, and the maximum number of colors that we could represent in a given computer pixel in a given portion of the screen is going to be 2 to the power of 24. And that's 256 to the power of 3, or this number right here. Anyways, now let's look at how binary is actually used to store data in a computer system and how it's used to store different types of data. So the first type of data we're going to talk about is going to be text data. Now, first, if we think about text, so let's say that this is text, right? Like just my name. So text is represented by a series of characters, and my name has 5 characters in it. And each one of these characters is going to be represented by a certain number of bytes and therefore bits, right? So A is going to be represented by a certain number of bytes. M is I, T, H, and so forth. And so basically to represent this character, we'd have one set of bytes, or we'd have one set of bits, right? For this one set of bits for this, one set of bits for this, etc., and they'd all be in the correct order. Now, how many bits and bytes? Well, let's just stick with bits, right? So how many bits represent each character depends on the format in which we are storing the text. So if we're going to use ASCII, then each one of these bits or each one of these characters is going to be worth 8 bits, okay? But if we use Unicode, then each one of these could be worth 16 bits or even more. So let's start with ASCII. So basically for ASCII, each character is represented by 8 bits. So you have 7 bits for each character, and then 1 bit, which is a parity bit, and that makes sure that the other bits have been transmitted accurately. And this means we have 2 to the power of 7, or 128 possible characters. If you look at this chart right here, which may be a bit hard to see, then we can see that these characters, this set of characters, not only includes letters and numbers, but also we have separate characters for lowercase, separate characters for capitals, lots for symbols, spaces, and punctuation. Even things for like shift out, like null, end of text, stuff that actually comes from like typewriters, weirdly. Like we have all of that stuff. We also have Denary and hex values that correspond to these bit values. And you can see those right here. I mean, they're still going to be stored in bits, but we also do have the equivalent Denary and hex. Now, the next type of format we're going to have is Unicode. And Unicode generally uses more than 8 bits. We do have Unicode 8, UTF-8, but more common is something like UTF-32 or UTF-16. And these can be used to represent a much wider range of characters, including like logos, but more importantly, characters in other languages, in languages other than English. So Chinese characters, Arabic letters, etc. Because Unicode gives us access to more bits in which we can represent characters, we can represent a greater combination or a greater range of characters, including letters in other languages. So if you compare both of them, each character can be represented by up to 32 bits in Unicode, and only 7 or in some cases 8 bits in ASCII. But Unicode can represent a much wider range of characters, including different languages. Now let's look at some practice examples which are connected to Unicode and ASCII. Again, this is just a small collection of practice questions. If you want to see more, go ahead and become a member to get access to more practice questions that are connected to each video. So first of all, state the number of characters that can be represented by the ASCII character set and the extended ASCII character set. So remember, for ASCII, we have 7 bits used to represent each character and 1 that's just a parity bit that's not used. So we can represent 2 to the power 7 or 128. Extended ASCII actually just lets us use 8 bits to represent characters. So that means that we have 2 to the power of 8 or 256 possibilities. But this, I think for the IB, you don't really need to know this one. So explain how a word such as house is represented by the ASCII character set. So basically what happens is that in order to represent house, we would find the bits, or we'd find the bit combination that corresponds to each one of these characters, and then put those 8 bits for each character in order. So we'd find out the 8 bits that correspond to H, and we would store that, and then after that we would store whatever corresponds to O, and then U, and then S, and then E, and together that would allow us to represent house using ASCII. So find the correct bit combination for each character, and then put those bit combinations in the correct order that corresponds to the order of the characters in that word. Okay, so next, here's an interesting one. Unicode is a different character set. The Unicode value for the character 1 is the Denary value 49. So write the hexadecimal value for the Unicode character 1. So essentially we need to convert Denary to hexadecimal. So we can just go ahead and do 16 to the power of 0, 16 to the power of 1, and actually like 16 to the power of 1, we can do 3 because that gives us 48. And if we do 49 minus 48, we only have 1 left, and that equals 1. So right here we can just put 1, and so our hexadecimal value is just going to be 31. Now next it says write the Denary value for the Unicode character 5. Now, like the values for these, the values for these characters are going to be stored in order, right? So if the Unicode value for the character 1 is the Denary value 49, that means 5 is just going to be like 4 places away in the set of Unicode values. So if we're using 49 to represent 1, or we can use 53 to represent 5. And one thing to understand about Unicode characters and just character sets in general is that different types of values are going to be stored together. So numbers are going to be stored together, different languages are going to be stored together, capital and lowercase are going to be stored together. And that's kind of why, like, if we have the character 1, then the character 5 is just going to be like 4 places away at the Denary value 53. And it's probably going to be a higher value as well because we're going up from 1, 2, 3, 4, 5. Okay, so now that we understand how text is displayed using binary, let's go ahead and get into how images are displayed. And in order to understand this, we need to go through a few things. So the first thing that we need to understand is that every display, so every monitor or phone screen, is divided into pixels. And a pixel is essentially a small square in a grid that is the screen. Now these pixels are usually quite small. Here we have an example of the size of a pixel. Pixels can vary in size, but in any case, a pixel is the smallest controllable element in a display. Every pixel has a single different color, and that color is going to be indicated by binary. And we can also say that each pixel has one color at one moment, and this is particularly necessary to understand if we're considering a computer screen, right, where we're opening different programs or we have video running. So every pixel has a different color, and that color can change from one moment to the next. Now this color is a combination of red, blue, and green, as we kind of saw in the practice question we just went through, the one that was connected to hexadecimal. And as we said before, this combination of red, blue, and green is controlled by some number of bits that corresponds to each pixel. A pixel is working together, so every pixel having a different color in a grid is what allows us to display images like this one. And this usage of pixels is connected to screen resolution. So you might have seen a screen having a resolution of 1024 by 764 or even more. That is referring to 1024 pixels high and 764 pixels wide. Now 1080p, HD, and 4K all refer to a number of pixels as well. Usually, and these are all going to be a higher number of pixels than this right here. Because the more pixels you have, the more detail which you can display images in video. So we're going to talk now a little bit about bitmap images, because bitmap images are the most common image formats in which we display, by which we display images. Some examples of bitmap formats or bitmap images are probably formats you've seen before, like JPEG, PNG, GIF, or BMP. Now these are used in all types of graphics, and essentially bitmap images are themselves composed of a grid of pixels, and each grid has its own intensity and its own color. Here we have a really simple example of a bitmap image that's used to display a picture on a screen. Now we can assume the screen is only displaying black and white, and we want to display this in digital form as a bitmap image. So as you can see right here, all of the white areas have the binary value 0, and all of the areas that are in black have the binary value 1. And this is a very simplistic example of how a bitmap image is displayed. Usually we're talking about images in color, and each one of these pixels are going to correspond to 8 or 24 or 16 bits. So more bits than we have right here because we just don't have a black and white image. So let's take a little bit closer look at pixels. So as we said before, each color in a pixel is represented by a certain number of binary values. So usually, particularly when working with bitmap images on a computer, each color is represented by a 6-digit hexadecimal value, which corresponds to about 24 bits. And these are examples of the types of hexadecimal codes we might use to display different colors. So the first two values in this hexadecimal code are going to represent red, the second are going to represent green, and the last two represent blue. Something like this. And given what we know about hexadecimal, that means we have this number of possible color combinations, right? So 256 to the power of 3 is going to be our possible color combinations. Now the next term we're going to talk about is going to be color depth. Now color depth here, I think it is quite well defined. Our color depth in this situation where we're using hexadecimal to represent colors, which is one of the most common situations, that means we're going to have a color depth of 24 bits, right? We have 24 bits to express the specific shade of the color that we want to show. And that is our color depth in that example, 24 bits. Here we have another example, and here as we can see in each pixel, we have 3 bits representing each pixel, representing the color in each pixel. And so that means that our color depth is going to be 3 bits, and accordingly, we have 8 possible colors that can be represented in each bit. And these are those colors, as opposed to the 24 bits we had in the other example, which allow us to represent a much greater range of colors. Okay, so to solidify our understanding of this topic, let's look at a practice question. A bitmap image has a resolution of 2048 pixels wide and 1024 pixels high. The image has a bit depth of 10 bits per pixel. Estimate the file size of the bitmap image in megabytes. Show your working. So one thing to know is that how megabytes work is by 1024. So basically 1 byte equals 8 bits. And 1 kilobyte equals 1024 bytes, and 1 megabyte equals 1024 kilobytes. Okay, so we're looking in terms of 2 to the power of something. So we want to figure out how many bits there are, and then figure out how many megabytes that is. So to figure out how many bits there are, we're going to do 2048 times 1024, because that gives us the total number of pixels in our image, and then we're going to multiply that by 10 bits for each pixel. And then we're going to divide that by the number of bits in 1 megabyte. So to do that, we're going to do 8 bits times 1024, for one kilobyte times 1024 for 1 megabyte. And we're going to get something like 2.5. So our answer is going to be 2.5 megabytes. Now, next question, state what is meant by the bit depth of a bitmap image and explain how changing the bit depth affects the image. So remember, bit depth is how many bits are used to represent a single pixel on an image. And if we have a greater bit depth, we can represent a greater range of colors in our image. If we have a lower bit depth, we can express a smaller range of colors. Next, explain why a bitmap image is often compressed before it's attached to an email. This is just so we can send the email more quickly, right? We reduce the size of the bitmap image, we can send it more quickly, and depending how it's compressed, the end user or the recipient can decompress that image to see it. Now next, one of the photographs has a bit depth of 8 bytes and an image resolution of 1500 pixels wide and 3000 pixels high. Calculate the file size in megabytes. So one thing to keep in mind is that if we're talking about megabytes, now we're talking about 1000 bytes. Okay, so we need to figure out how many bytes this is and then see how many megabytes that's going to be. So first off, it has a bit depth of 8 bytes, which means 1 pixel is represented by 8 bytes, which is actually, that's pretty good. That's going to be, yeah, like 64 bits. So we're going to do 1500 times 3000 for the number of pixels, and we're going to multiply that by 8 bytes. And then to get the number of megabytes, we're going to divide this by the number of bytes to get 1 megabyte. And so that's going to be, so we have 1 byte times 1000 for a kilobyte times 1000 for a megabyte. And that should give us about 36 megabytes. Now let's take a look at some factors that can affect image quality, specifically bitmap image quality, which is going to be the main type of image format that we're talking about. So the first is the number of pixels. So the more pixels that are in an image, this means that we have more, we can express an image with more detail, right? Because we have more squares that are used to represent our image. So we have higher detail and smoother transitions between colors. So we're not abruptly changing, for example, green to red. We have enough pixels to make a transition between those colors and show something that isn't pixelated, right? Next, image resolution. So the higher the image resolution, the more pixels per inch or per given area, the more detail we can represent an image in, and the clearer image will be. Screen resolution means that we can better display high resolution images. So if our screen resolution is less than our image resolution, we may not be able to represent that image in full detail. And finally, we have color depth or bit depth, which allows for us to display an image in a greater range of colors and perhaps more accurately represent that image. So additionally, if we have lower bit depth, we can also get banding, which is what we see right here. We just get less realistic images if we can't represent the colors that we need to. Now, also, we can take a look at some factors that affect the file size of images. So more image resolution is going to increase the file size because we have more pixels, each that are represented by a certain number of bits. Higher screen resolution can increase file size if this leads to images being created with higher resolution. And higher bit depth means more data per pixel, and that's also going to increase our file size. Okay, guys, now let's take a look at our last practice exercise, and it's going to test our understanding of how file size is determined of images. So first, we have some scenarios here, and these scenarios are based on a file that has, it's 496 by 496 pixels with a color depth of 24 bits per pixel. So first, what happens if we change the color depth of the image file to 16 bits per pixel? And that's going to decrease the file size because we're going to use less bits to represent each pixel. Next, what if we change the screen resolution to 1366 by 768 pixels? Now, this actually isn't going to affect our file size at all because we're not actually changing the size. We're not changing the resolution of the image. We're just changing the resolution of what's going to display it. So we're not going to have any change in file size, but we just may not be showing that image in its full detail. Next, change the color of the rectangle from black to red. Yeah, that doesn't have any effect at all. Okay, so now that we've talked about how images are represented using binary, let's go ahead and see how sound is represented. So the first thing we're going to talk about is how sound is recorded and turned into a digital format, like WAV or MP3 or FLAC, which you probably never heard of FLAC before. Anyways, so basically what happens is audio is a sound wave, right? And what we do is we look at a sound wave like this, and basically what we hear is based on the amplitude. So it's based on the height of our sound wave at any given point in time. And so if we're recording audio, if we're taking audio and we're turning that into a digital format, what we're going to do is we're going to sample. So we're going to take the height of our sound waves at different intervals in time. So it may not necessarily be at the top or the bottom of the wave. I know there's a word for that. I can't remember what it is, but it might be just at certain points in time, right? So it might be right here. 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 There are different rates at which we can sample amplitude of the sound waves that we're recording. And some common sampled rates include 44.1 kilohertz or 48 kilohertz. And a hertz is just going to be one sample per second. So if we have kilohertz, that's going to be 1,000 samples per second. So this means that we're taking 44,100 samples per second, and we're getting the amplitude at per second. We're getting the amplitude at 44,100 points when we're recording. Now, each time we take a sample of the amplitude, we're going to store that as some value, and that value is going to be rounded based on how many bits we have. We ultimately have to store that in binary. So when we do quantization, when we just store an amplitude as a value and then round it, that's not necessarily going to be in binary, but we're going to be, the size of that value is going to depend on how many bits we have in order to store each amplitude. So we have sampling and we have quantization, where we just get an idea of the amplitude and we round it to the nearest value based on the range you've been given. And then we do encoding. So we take those quantized values and then we turn those into binary, and that binary is going to be, and basically what that binary format looks like is going to depend on the audio format, right? So it might be WAV, which is uncompressed. It might be MP3, which uses lossy compression, or FLAC, which uses lossless compression. But the point is, we're going to take all of these different amplitudes, turn them into binary, and then we're going to store them into some format that may or may not be compressed in some way. Now, that's how we turn audio that we hear, or that's being played, into a digital audio file. Now, if we're going to go the other way around, if we just want to play back audio, that digital data is going to be converted back into an analog signal. So it's going to be converted back into amplitudes, and those amplitudes are going to be output as sound through speakers or on our headphones. So to turn audio into a digital format so we can store it in a digital file, we're going to be sampling. And then to play it back, we're going to be looking at what those different samples are in order to represent the audio as it was recorded. So just to kind of summarize this whole process, amplitude is recorded a certain number of times per second. Oftentimes is recorded like 44,100 times per second. Not always, but often. And each instance is given a corresponding value, which is not initially binary, but then eventually becomes a binary number. And those binary numbers are saved in sequence so that like you actually hear the music in sequence, right? So people are singing when they're supposed to be singing, like you hear the music in the correct order. Now here's some important terminology in order for us to be able to understand this process and describe it. So first we have sampling, and that's the process of converting sound waves into discrete digital values by measuring amplitudes, right? So that process of measuring amplitudes, that's going to be sampling. The sampling rate is the number of samples taken per second, measured in hertz. If we have more sample rates like this, we can represent audio in more detail. Sampling resolution is essentially our bit depth, but as it applies to audio. So it's how many bits is used to represent each sample. And higher bit depth means more accurate representation of the sound at that particular point. So basically, if we have more bit depth, we have a greater range with which to represent particular sounds, and therefore we can have a more accurate representation. Now, if we're talking about analog data, we're talking about continuous sound waves that are being naturally generated through variations in air pressure. So if you're just playing the guitar, you're generating an analog signal. It's a continuous signal, and that's because you're changing air pressure. Now, discrete digital signals are different because they are a numerical representation. So they're representing sound not as continuous waves, but discretely by storing sound at multiple points in the form of binary. And this binary is processed and stored in order to record audio, and is read in order to reproduce audio as something that resembles an analog sound wave. But it's still never going to be as good as an analog sound wave because ultimately it's taken based on sampling. However, because our ear can't really distinguish beyond a certain rate, we may not notice it. Now let's take a look at some factors affecting the file size and accuracy. So if we have higher sampling rates and or higher sampling resolutions, that's going to take up more data. but that's gonna increase file size. But also, like, higher sampling rates and resolutions mean we have higher accuracy because we're more frequently recording the sounds we're hearing, and we're recording them, and we have a greater range at which to record those sounds, which means that we're going to have finer granularity, right? So we're going to be able to replicate that sound digitally with just greater detail at each given point. So now that we've gone through sound, let's take a look at video. So video is actually not like storing video files is not that different from storing images, because a video is just a collection of images called frames. And each frame is made up of pixels, right? And in each pixel, there's a certain number of bits. So essentially, like, we just look at how many pixels and what the bit depth is for each frame, and then we multiply that by the number of frames we have, which can be lower or higher depending on how we're representing our video. And that's going to give us a stored size for video. And oftentimes frames are compressed using algorithms in order to be able to allow us to easily transmit or play back a video. So if we want to calculate video file size, we look at frames per video, pixels and color depth, and then compression. So this is going to give us the size of the raw video file, and then it's probably going to get compressed in some way to give us our final video file size. Okay, to finish out this section on how video is displayed using binary, let's go ahead and let's solve a really quick practice question. So a video is recorded at 30 frames per second for 20 seconds. Each frame has a resolution of 1280 by 720 and uses 24 bits per pixel. After encoding with H.264, the video achieves a compression ratio of 20.1. How many megabytes does the final file take? So we're going to do two things. The first thing I want to do is I want to calculate how many frames there are, okay? Because that's essentially how many pictures or how many images there are. So you have 30 frames times 20 seconds, which means that we have 600 frames. Now we see that each frame has a resolution of 1280 by 720 and uses 24 bits per pixel. So now what I want to do is calculate how many bits there are per frame. So I'm going to do 1280 wide by 720 high times 24 bits for each pixel. And I'm going to end up with 22,118,400 bits. But now to get the total number of bits in our file, I'm going to have to multiply these two, frames times the number of bits per frame. So if I multiply 600 times this, then I get a total number of bits of 13 billion 271 40,000. And remember, we're going to compress this. So we have a compression ratio of 20:1, which means I can just go ahead and divide this by 20 to get the actual number of bits. But first, I think probably what we're going to do, and this is probably just the easier way to do it, is we're going to convert this to bytes. So this is bits, and if we convert this to bytes, we're going to divide by 8 because 8 bits equals 1 byte. And that's going to give us 880,000. And then for compression, we're going to divide that by 20. If you divide that by 20, we end up with 944,000 bytes. And now we want to figure out how many megabytes this is. And basically to figure out how many megabytes this is, we're just going to divide this by 1 million. Because 1 byte, so it's going to be like 1,000 bytes to 1 kilobyte, and then 1,000 kilobytes to 1 megabyte. So we can divide by like 1 million, and we end up with 82.94 megabytes, which we could just round up to 83 megabytes. And that's essentially the file size of our 20-second video, which actually, if you think about it, or if you've worked with video a lot, that actually makes quite a bit of sense. Okay, so now that we've covered how binary is used to represent different types of data, we're going to get into the next topic, or broad topic that we're going to cover in this video, which is going to be logic gates. So logic gates are essentially switches that lead to different outputs based on their input. Now, processors and chips are made up of millions of these logic gates, hence the reason why we're going to learn about them. Now, each logic gate takes 1 to 2 inputs and has 1 output. Possible inputs are 1 or 0, which correspond to binary values. And 1 might be indicated by a high voltage or a relatively higher voltage, and 0 might be indicated by a relatively lower voltage. And voltage is just pressure, the pressure at which electrons flow through a circuit, and that's how they're going to be detected as to whether they're high voltage or low voltage by our logic gate or a switch. So a logic gate is essentially just a very, very small silicon device that can help detect voltages and give us an output based on the type of voltages that have been input into its wires. Now, generally in chips and in circuits themselves, logic gates are used to carry out basic logical functions like and, or not. This allows our circuits or our chips to be able to make decisions. And these can often be combined into combinations, as we said, of even millions of logic gates to allow us to execute very complex logical operations. At the end of the day, these types of logical functions are used to perform calculations and control tasks within the computer based on certain inputs. Okay, so now that we understand what logic gates are at a basic level, let's go ahead and see how they're represented and how we'll be using them in the IB exam. So we have a variety of logic gates we're going to have to learn about, and the first is going to be the NOT gate. Now next to the NOT gate, we have something called a truth table right here, and this shows all the possible combinations of inputs we could have. These are all truth tables, as well as the corresponding output for each of the respective combinations. Now, a logic gate can either have one or two inputs, but most of them have two inputs. Each input can either be a 0 or a 1. Hence why in our input columns we have 1s and 0s. Now if you look at our NOT gate, what a NOT gate does is it reverses any input that's put in. So if you put in a 0, we get a 1. If you put in a 1, we get a 0, as we can see right here from our truth table. This is probably the simplest possible logic gate. Now our next type of logic gate is slightly more complex, and it's an AND gate. This AND gate has two inputs, which we can call A and B. And right here we can see in our columns the different combinations of A and B that we can possibly have. What we notice here is that the only time that our output is going to be 1 is right here, where both the inputs are also 1. If we have any combination of other inputs, then our output is just always going to be 0. Now next we have the NAND gate, which is essentially the reverse of the AND gate. And NAND is not AND. So if you look at our outputs right here, we have 0, 0, 0, 1. If you look at our outputs for the same inputs, we have 1, 1, 1, 0. In fact, the only time we get a 0 is when both of our inputs are 1. For all other inputs, we're going to get 1s. One thing to keep in mind as well is we can see how these are represented, right? We have a NOT gate represented like this, an AND gate represented like this. You're going to have to be able to draw these gates. Now, a NAND looks interesting because we have the AND right here, right? Then we also have the circle right here. And the reason is because a NAND gate is essentially an AND gate with a NOT in front of it, right? Because remember, we talked about how it's basically giving us the exact reversed outputs for the same inputs into the AND gate. So this right here is going to be the same thing. Now, next we have the OR gate. Now, the OR gate is only going to give us a 0 if both inputs are 0. For any other input, we're just going to get a 1. So basically, if we have a 1 anywhere in our input, then our output's going to be a 1. In the AND gate, if we have a 1, or if we have anything but two 1s, then our output is going to be 0. So AND gate, if we have a 1 anywhere in our inputs, then our output's going to be a 1. Otherwise, we're going to have a 0. And accordingly, we have our NOR gate, which again is a similar concept to the NAND gate. So for the same inputs, our outputs are the opposite for our NOR gate. So the only time we have a 1 is when we don't have any 1s in our inputs. And again, this is similar in that this is basically an OR gate with a NOT gate in front of it. Now the last type of gate that we're going to look at is going to be our exclusive OR gate. And this is also called an XOR gate. And basically how this works is that if we have different inputs, we're going to have a 1, otherwise we're going to have a 0. Remember, this is drawn a little bit differently, right? It looks like an OR gate, but then we have this little thing right underneath it, so bridge right underneath it. We have an exclusive NOR gate, which is just the opposite of an XOR. So right here, we only have a 1 if our inputs are the same, otherwise we have a 0. Now another useful way to think about this is a 0 being a false and a true, but it doesn't really matter as long as you understand what your inputs and outputs are supposed to be. So now we understand how logic gates work based on logic gate notation. So based on how logic gates are represented here, let's go ahead and let's draw them. So right here we have the circuit X or not Y. So we're going to have two inputs. We're going to have X and Y. And what's important to note is that when we draw these logic gates, we're going to start with the closest gates to our inputs. So right here we have or next to x, but right here we have not next to y. So that not is going to supersede anything else that's coming before the or. And so we're going to have not y and x that are united by the or gate. The or gate's going to go in the middle. So we're going to draw a not gate in front of the y. And then these are going to go together. That's an or gate. And this is just going to be our logic circuit. Okay. Now you don't have to write the or, I just did that to make it clear. So that's what our first logic circuit's going to look like. Now for our next logic circuit, again, we're going to start on the outside. We're going to start next to our inputs and then work our way in. So we're going to start with not C and with A XOR B. So right here we have three inputs to our circuit. So we're going to draw them all out, A, B, and C. So we can go ahead and draw A XOR B, which is going to look like this. So we have it looks like an OR, but then there's like a little thingy underneath. So that's our XOR. And then we have C, which is just going to have a not in front of it. And I'm going to bring that a bit closer in here. So we got a not right there. And they're united by an AND. So A XOR and not C. So that's going to go right here. Actually, that's going to be flat like that. And that's going to be our AND gate. And this is going to be our logic circuit. Now, again, if you're bad at drawing, just make sure and write what the actual logic gate is so you can just make it clear. Now, our last example, it's a bit longer right here. Okay, so we're going to again start on the outside and work our way in. So we have three inputs. We have A, we have B, and we have C. So we'll start with A or B, and we'll do what we did before. And we have not A and C. So we also need to draw A and C. And the way we're going to do this is we're going to take that same input from A, and we're going to draw a wire from A before it goes through a gate over here. We're going to draw an AND gate between A and C. Okay. And there's also a NOT gate. The next thing we have right there is a NOT gate, right? So this is going to be AND, and then we're going to draw another NOT gate. And then this side and this side are united by another AND gate. So we're going to draw those going in together, and we have an AND gate, and this is going to be our logic circuit. So now that we've actually drawn some logic circuits, let's look at the logic circuit and let's actually write out the expression. So right here we can see we have three inputs and we have an output of x. So we can go ahead and write x equals here. And remember, we're going to start on this side. So we're going to start on this side of the logic circuit and then work our way in. So let's see what's happening on this side. So first off, we're starting out with, we have A and B. So we can go ahead and write that. We have A and B. Also right here, we have B not C, or sorry, we just have not B, which is going on. And we have like the output of A and B, and that's going through our OR gate, or our XOR gate. So the interesting thing is we have both A and B, and the result of A and B has an XOR with C. So we're just gonna go ahead and write that out. And the thing is, we're gonna do that first because the result of this XOR, so like right here, that's going to be united by the OR gate with B, which is coming down from right here, with not B. So this whole thing is going to be united with not B, which is why we're going to go ahead and do that first. And you kind of have to analyze the logic circuit to get a feel for how to do this. But it still does help to start on this side and then work your way in. So we have A and B XOR C, and that's going to be united through an OR gate. So we're going to have OR, not B, because the result of this is going to have an OR gate with not B. Now, next we're going to look at some logic circuits and truth tables. So here we have a simple OR gate and then a NOT gate. So we have the two inputs, we have A and B, right? And we have every combination of A and B. And then we also have C, which is just going to be right here. This is going to be before we go into the NOT gate. Now remember, in an OR gate, every combination of inputs that contains a 1 is going to give us a 1. And the only time we're not going to have a 1 is when we have two zeros. So immediately you can put a 0 right here, or you can put a 1, 1, and 1 right here. But remember, that's going to be the output right here. Then it needs to go through a NOT gate to get to Q, which is our output right here. So the C is going to go through a NOT, whatever signal is at C is going to go through a NOT gate, and it's going to get reversed. So our output's ultimately going to be 1, 0, 0, 0. This also makes sense because you can see this is actually really a NOR gate. Now next we have a slightly more complex version of this gate. So we still have an OR gate right here. And so it's C, we're still going to have an OR gate. So we can go ahead and fill that in. We're going to have 0, 1, 1, 1. But then right here we have D, which is the same as B, right? So D is basically connected to the B wire. And so right here, D is going to be the same as B. So we can just go ahead and copy that. 0, 1, 0, 1. And then both C and D are going through an AND gate. Remember, in an AND gate, the only time we have a 1 is when both inputs are 1. So we can fill this out, and the rest are going to be 0. And so Q, our output, is going to be this right here. Now we have our last and most complex truth table example, although to be fair, these truth tables are going to get much bigger later on. So again, we have A and B, and we're going to fill in. We don't have B pre-filled in for us, so we're just going to fill in all the possible combinations of B and A. So we're going to have 1, 1, 0, 1, 0. And so C is pretty much going to be the same, right? It's going to be it's going to be the OR of A and B. And remember, for OR, the only time we have a 0 is when we have two zeros. So we're just going to have right here 1, 0, 1, 1. Actually, I think it might be a bit easier for me to just keep things like sort of consistent. 0, 1, 0, 1. Just because it looks the same as it did before, right? So this is going to give us 0, and the rest are going to give us a 1. I mean, both are correct, but I think this is just easier to keep track of things. And then D is basically going to be whatever is going to be right here. So it's going to be whatever is in the B column, but it's going to be the reverse because we have a not in front of the B signal, or in front of the B input. So this is going to be 1, 0, 1, 0. And here we have an XOR. Remember, in an XOR, if the inputs are different, then we have a 1. Otherwise, we have a 0. So right here, we're going to have a 1. Right here, we're going to have 1. Right here, we're going to have a 1. And we're going to have a 0 right here because the inputs are the same. Okay, so right here, when I was talking about having a larger truth table, now I actually this is from the A level. I saw one example on the IB exams for the previous curriculum, like only one example, like from all of the exams for like the 14 years where that curriculum is being followed, which makes me think that it could actually be on the new curriculum because that example was literally on like the 2005 exam. So I think it's worth understanding how to do this. I mean, it's not more difficult than what you did before. It's just slightly more complex. So essentially you have a truth table for a more complicated logic expression right here. And you have 3 inputs right from the get-go. And these are all the combinations. This represents the combinations of all 3 inputs, right? For A, B, and C. Now, if you need to fill this in yourself, kind of see how we start out with in the first column, half zeros, half ones. 2 zeros, 2 ones, 2 zeros, 2 ones, and then we alternate between 0 and 1. This is a good pattern to follow in general. So just keep that in mind. Now, the way we're going to do this is similar to how we actually drew logic circuits. We're going to start from the inside and work our way out. We're going to start from the outside and work our way in. So we're going to start with what A XOR B and B XOR C is. And then we're going to go to, well, okay, let's start with that. And actually, I think what I want to do, the way I want to handle this is, just for saving space, let's call this, actually, never. I was going to give this like a code name, like X. Well, actually, let's call this X and Y to keep things simple. Actually, no, we have an input X, so let's call this E and F. So E is A XOR B, right? So remember, A XOR B is only going to be a 1 when both inputs are different. So right here, it's going to be a 0, a 0, a 1, a 1, a 1, 1, 0, 0. Now next we have B XOR C, which we're labeling F, right? And so same principle, we have an XOR gate. So here we're going to have 0, 1, 1, 0, 0, 1, 1, 0. Now next we have A and F. So we have this right here. Okay, so you have this whole expression right here. So we're going to do that. We're going to say A and F, and that's going to be our next column. And actually, I want to call that whole thing G. So that whole grouping, so G is going to be equal to A and B XOR C. I probably could just say A and F, but anyways, this is probably just going to be a bit more concise. So let's call that G, okay? And G is essentially going to be G is going to be equal to A and F. So we need to look at A, and we need to look at f, and then we need to pick out, we need to see, remember, like if you have an AND gate, the only time we're going to have a 1 is when both inputs are 1. So right here, 0, 0, 0, 0, 0. Okay, we got a 1 right here. Another 1 and 0. So that's G. And now we're just going to have E and G, right? So we're comparing, or essentially we have a NAND gate between these two, between this expression and this expression right here. So essentially our last column is just going to be like, it's going to be E NAND G. Remember, NAND is like the opposite of AND. So that means that the only time we're going to have a 1 is when our inputs are not both 1. So we're going to be looking at, let's just choose a different color. Actually, we can just use purple for this, right? So we're going to be comparing E and G. And so if we have 0, 0, that's going to be a 1. If we have 0, 0, that's going to be a 1. If you have 1, 0, that's going to be a 1. If you have 1, 0, that's going to be a 1. 1, 0 is going to be a 1. 1, 1 is going to be a 0. 0, 1 is going to be a 1, and 0, 0 is going to be a 1. And actually, E and G, that's actually like, that's the same thing as this. I could have just put this here, right? Because that's ultimately what X is. So it's just the same thing, right? So 1, 1, 1, 1, 1, 0, 1, 1. And the reality is, like, you're usually not going to get points for your working space, but it really just helps to have an organized working space to keep track of things. Okay, so let's take a look at some more advanced problems involving logic gates and logical expressions. So here we have a fairly complex logical expression. We're going to draw the logical circuit. And this is pretty complex. We have an expression in a set of parentheses here, and an expression in a set of parentheses here. And then these are both in a larger set of parentheses right here that's connected to the input P by an AND gate. So let's start with these right here. So you have Q or not R. So we're going to start with Q, and then we have not R, and this is connected by an OR gate. And then we have P XOR Q. So we're going to draw a little wire from Q. We're going to connect that to P in an XOR gate. Okay, that's an XOR gate. And then both of these are connected to each other through an XOR gate. So we're going to draw another XOR gate right here. And the output of this is going to be connected to P via a NAND gate. So we're going to draw another wire from P. And we're going to draw our NAND gate, which is just an AND gate with a circle on top. And we're going to hook that up to W. Okay, so now we're actually going to use logic gates to model a real-world problem. And so here we have a car that has features that monitor speed, direction, and distance. So essentially, our car is going to be giving us 3 inputs. It's going to be giving us input A, B, and C. And these inputs are going to go into a logical circuit that we're going to design. So A represents the distance from the vehicle in front, with the input being 0 if it's less than 20 meters from the vehicle in front, and 1 if it's 20 or more. B giving a 0 if the car is traveling in reverse or stationary, and 1 if it's traveling forward. And C giving us a 0 if the car is traveling more than 130 kilometers per hour, and 1 if it's traveling 130 or less. So here it says construct a logical diagram with inputs A, B, and C and output Z to represent the following scenario. We're going to say output Z equals 1 when the car is traveling forward and it is less than 20 meters from the vehicle in front, or the car speed is more than 130 kilometers per hour. So I'm going to go ahead and write down what the binary input is going to be in each of these situations, like what we'd expect. And remember, when we take this input in, we're going to expect an output of Z, and we're going to design the logic circuit as such. So the car is traveling forward is going to be this condition right here, where B equals 1. It is less than 20 meters from the vehicle in front. That is going to be this right here, where A equals 0. And our third condition is going to be the car speed is more than 130 kilometers per hour, and that's going to be C equals 0. Remember, these conditions 1 and 2 are united by an AND gate, right? Because the car is traveling forward and it is less than 20 meters from the vehicle in front. And then the output of that is connected to condition 3 by an OR gate, because we have an OR right here. So let's go ahead and model this. We're going to go ahead and draw our inputs, A, B, and C. And what's important to remember is that B equals 1 means that we're not going to do anything further with that input, But if A equals 0, we're going to draw a NOT gate. And if C equals 0, we're going to draw a NOT gate as well. The reason we're doing this is because we want our output to be Z equals 1 in the given condition and Z equals 0 in any other conditions. For this situation, we're going to unite A and B by an AND gate, and that's going to be united with C by an OR gate, and that's going to go out to, our output's going to be Z. So we're going to have one more problem like this just to solidify your understanding. So here we have a wind turbine system, and it has a safety system with 3 inputs to a logic circuit. Each of those inputs represent turbine speed, bearing temperature, and wind velocity. And these conditions, we want to have an output of 1 based on these particular conditions. So we're going to go ahead and label these 1. Remember, 1 and 2, 3 and 4, 5 and 6, each of these are united by an and those conditions are united by an OR. So we need to have either this condition or this condition or this condition. But for like 1 and 2, turbine speed needs to be less than or equal to 1000 RPM and bearing temperature. So we have ands right here and ORs between those conditions. So let's just go ahead and write these out. 1, turbine speed is less than or equal to 1000 RPM. That's S equals 0. 2, bearing temperature is greater than 80 degrees Celsius. That's T equals 1. 3, speed is greater than 1000 RPM. That's S equals 1. 4, wind velocity is greater than 120 kilometers per hour. That's W equals 1. And 5, bearing temperature is less than or equal to 80 degrees Celsius. That's going to be T equals 0. And 6, wind velocity is greater than 120 kilometers per hour. That's going to be W equals 1. So these are united by AND gates, right? And then, so let's go ahead and just do that first. So we're going to go ahead and draw our inputs S, T, and W. So first you have S equals 1. So I'm going to go ahead and write that out actually. You have S equals 0 and T equals 1. So remember, S equals 0, NOT gate. And that's going to be joined with T equals 1 by an AND gate. And then we have S equals 1 and W equals 1. So we can go ahead and just draw a wire from there to W. And we have another AND gate. And then lastly, we have T equals 0 and W equals 1. W equals 1. So what I'm going to do is I'm going to go ahead and just draw a wire from there with a NOT gate. And that's going to go, we're going to draw a wire from W. And then we're going to have another AND gate right there. Remember, all of these, so each of these are joined by OR gates. So we're going to go ahead and we're going to unite these two by an OR gate. And then the output of that is going to be united with this by an OR gate. And our output is going to be X. And that's basically how that's going to work. So big thing, if we have S equals 0, or if we have something equaling to 0, you're going to use a NOT gate. If not, then you're just going to use a wire, and you're going to look at the conditions that are given to us in order to construct your logic gate. Anyways, that's it for these types of problems. Let's move on. Okay, so in the next part here, we're going to talk about Boolean expressions. Right here, if we look back at a previous slide, we have a number of expressions that we've used to describe our logic circuits, okay? And these can also be termed as Boolean expressions. They're Boolean expressions because essentially we are representing variables. We have variables here that can represent true or false, where in the case of our logic circuits, true would be 1 and false would be 0. That makes these Boolean expressions. Now we can use notation to represent Boolean expressions. So the way we could represent this could be x plus y. Okay, and the bar above the y means not, and the plus means or. So these represent logic circuits, but they're also Boolean expressions. They're basically one and the same. If we want to represent a more complex logic circuit using Boolean notation, we could just do x, a. We have a circle with a plus inside of it, b, to represent a, x, or b. And we don't really, and is just going to be a space, so we can just put not c right here. And similarly right here, we could say a plus b, and then we can do ac, not ac. Now, as you can see, we can end up with some pretty complex expressions that are representing our logic circuits. One thing that we can also do is using Using some basic laws of Boolean algebra, because yes, this is going to become algebra, we can go ahead and we can simplify some of these larger expressions we have. And we can get simpler expressions that represent simpler logic circuits, but are equal to the same thing we started out with. So let's look at some examples. So the first example we're going to look at is going to be A plus B. And if we were to look at this in our previous notation, this would just be A and A or B. So that would represent a logic circuit where we would basically have, remember we'd start with our parentheses, and we would have something like, well, we have two inputs, we have A and we have B. So A and A or B means that we'd have an OR gate, and then we'd have A, this would be a AND gate, and then that would be our answer. Let's say if this is X, we'd have X equals that, right? So these right here, one and the same. And this is the logic gate that represents this Boolean expression. So as an input to A, we'd have one, maybe 1 or 0 or whatever. Remember 1 being true and 0 being false. But this whole like logic circuit here can actually be represented much more simply. And we can figure that out by using Boolean algebra to simplify this expression. Let's see how we can do that. So the first thing we're going to do is we're going to take a look at our table right here, okay? And we can use something called the distributive law. So if you use the distributive law, we can see how a expression structured like this can turn into something else. So A times A and A or B could turn into AA plus AB. And if we look at our idempotent law right here, A and A, because that's what this is, right? This right here is A and A, can just turn into A, right? Because, I mean, if A is true, I mean, really, if like these are essentially the same input. So it makes sense that A and A would just give us A, right? They're going to be the exact same thing. Like if this is 0 and this is 0, then we're just going to end up with 0. We're never going to have a situation where we're going to have like, and we're going to have something drastically different. So that's kind of how we can think about some of these laws. We need to think about them in terms of Boolean values, in terms of zeros and ones, or we can even say true and false. But so we end up with A plus AB. And now we've already gotten a bit simpler, right? But we can look at what we have right here in this table and we can go even simpler. So right here we have this absorption law, okay? And it's essentially identical to what we have right here. And we can see that A or A and B, so A plus AB, is going to equal to A. So essentially what that means is that this circuit right here, A plus B, is the same thing as just having an A input. It's basically the same thing as just having this and really even no gates around it. It's the exact same thing. So maybe that didn't make much sense. So let's go ahead and let's look at another example. Now next we have A. Now next we have A plus A, not A, B. So A or, I'm just going to go ahead and again write this out. A or not A and B. That's what this is. So let's see how we can simplify this down to a simpler logic circuit. Okay. So first thing we're going to do is we can actually apply something called the distributive law. So right here we have, again, this expression right here represents our situation. Okay. So this is going to turn into, or sorry, rather it's actually this one right here. So this is going to turn into A plus A and A plus B. So now we just need to simplify this down. So if you look at the inverse law right here, this is just going to give us so A plus not A, so A or not A is just going to give us a 1 or a true. So we're just going to have true and then and A or B. But when we're doing this, that true is just going to drop off, so that doesn't really matter. And then we're going to have just A plus B, and this is going to be our output. So that means that this circuit is equivalent right here to this right here. Now let's look at one more complex example in order just to give you an idea of how this works. So right now we have ABC plus AB not C plus A not B. So A and B and C, or A and B and not C, or A and B. So the first thing we're going to do is we're going to go to the distributive law. And for the first two expressions, we can distribute out A and B. So what this is going to give us is AB. And well, really what's going to help is going to be this part right here, right? So AB and C plus not C plus A, or actually this in the problem itself, this one was supposed to be A not B, my bad. So A, B. I mixed up writing that. And we can see right here that when we have C plus not C, we're going to end up with AB. And then that's just going to be 1, which is going to drop off. So you end up with A and so AB or A and not B. And then using this formula again right here, we can do A, B plus not B. And going back to our inverse law right here, we just end up with A. So really what was a pretty complex gate was just equivalent to A. Anyways, using these laws, which you should be familiar with, is how we can actually simplify Boolean expressions, which is asked for in the IB curriculum. Now, again, if you want to see more solved examples of this and more information on how this is approached in the IB exam, then please feel free to check out the video in the link, which is accessible to members. Anyways, now that we kind of understand how Boolean notation works and how Boolean algebra works, let's move on to the next topic, which is going to be Karnaugh laws. Or rather, it's called Karnaugh Maps. So what we're going to look at first is a truth table. Now, as you can see, this is a truth table for a fairly complex circuit, but using a form of Boolean expression called sum of products, we can actually represent this in a fairly simple way. So first off, we're going to look at those rows where the output is 1. So we have this row right here, this row right here, right here, right here, right here, and right here. And remember, these are basically what we care about in defining this logical circuit. And what we can do is we can write an expression for every single row or every single set of inputs that leads to the output being 1. So let's start with the first row. Okay, we have 1 for A and 1 for C. So that means the way we can write this is we can write this as A, not B, C, not D, because B and D are both 0. We can go to our next row, and all inputs are 1 except for B. So we can say or A, not B, C, and D. And next, you can look at, we see that the first two inputs are 1s, and the rest are not. So we can represent this row, this set of inputs, as AB, not C, not D, plus, you can kind of see how this goes, right? And this is the expression that we can basically use in order to be able to represent this truth table and the logical circuit that's represented by this truth table. Now, I'm going to show you one more example because this is actually pretty important for being able to create Karnaugh maps. And we'll see what those Karnaugh maps are in a second. So again, we're going to look at this truth table. Remember, the key is to identify where the outputs are 1s or true. Okay. So first off, we have, and now we can go ahead and write our expressions. And there we go. This is the correct expression. So now let's look at a Karnaugh map itself. This is the first time we're looking at a Karnaugh map, or we're going to call it a K-map from now on. And here we have a sum of products expression similar to what we've seen before. So the goal of a K-map is to take this and simplify it down, okay? And so right here you can see that you have, basically, you have a grid, and on the horizontal part of the grid, you have values that are representing AB, and on the vertical portion of the grid, basically the y-axis, if you will, you have values that are representing CD. So in this grid, we're going to put ones and zeros based on what the values of A, B, and CD are. Okay, a 0 for a naught, and a one for a value that doesn't have a naught. So for example, if you look at this right here, okay, so this is going to be, we have for AB, we have 0, 1. So it's going to be in this row right here. And then we have 0, 0 for CD. So we're going to write a 1 right here in our Karnaugh map. And we're going to repeat this process for every single part of this expression. So right here, we're going to have a 0, 1 for AB. So it's still going to be in the same row. And then we're going to have a 0, 1 for CD. So we're going to have a 1 right here. Next, we're going to have 0, 0, or we're going to have 1, 1, and 0, 0. So 1, 1 for AB, and then 0, 0 for CD. So we're going to have a 1 right here. Next, we have 1, 1 for AB, and 0, 1 for CD. So we're going to have a 1 right here. Next, we have, we got a 1, 0. So it's going to be in this row, and then a 0, 0. So right here. And finally, we have right here, we've got a 1, 0, and then a 1, 0. So, or sorry, a 0, 1. So that's going to go right here. Now, there are a few rules. Well, basically, okay, so this is where ones are going to be, and everything else is going to be 0. Now, what we're going to do next is we're actually going to put loops. And where we put loops, this actually follows a few rules. So we can only make groups of ones, first of all, in our loops, which are going to look something like this. Okay. We can only make groups of 2 n size. So we're talking about like 2, 4, 6, 8, for example. Groups can only be column, rows, or rectangles. Groups can overlap, but should as little as possible. And the fewer groups, the better. So right here, we have, you can kind of see how that was done right here. We have a group of ones right here and a group of ones right here. And this was probably a smaller truth table. So we had basically a set of expressions that only involved 3 inputs. So if you look right here, we need to follow our rules, right? So we can only basically have groups of 2 n size. And we want to have as few groups as possible, which means looking at this Karnaugh map, we're probably going to have 2 groups of 4. So this is going to be our first loop, and this is going to be our second loop. If we had groups of 2, then that would be too many. We don't need that many. If you had one group of 6, that wouldn't follow our 2n rule. So now we have these two loops. And what can we do with these 2 loops? Now, in the first loop, what we're going to do is we're going to see what the common values are for A and B. Right now, we can see that for A changes, right? So we have 0 for A in one column, and we have 1 for A in another column. So that's not common within our group, within this first group. But B stays the same. So we can go ahead and we can just write B off to the side. And for the same group, we can see that if we're looking at the vertical portion, right, that C is going to change, or sorry, D is going to change, but C is not, and C is always going to be 0. So we can write not C to represent that. But we have 2 groups, so we're going to have an OR, and then we're going to look at the next group. So if you look at the next group right here, so that's going to be this group right here, we can see that B is going to change, but A is going to stay the same. So we can have A. And we can see if we're going vertically that C is also going to be like so. So right here in this question, it's asking us to write the simplified sum of products. We're going to end up with AC plus BC. And now we want to simplify it down. So we'll look at our table and remember this. So we end up with A plus B, C, and that's going to be our simplest form. And that's when we make use of a Karnaugh map. Now, I know that first example may have been a bit complex, especially since it was your first time seeing that. So let's go ahead and let's look at a few more examples. Okay, so let's look at the next K-map. So right here, you can kind of see what we have. We got 0, 0, 0, right? Because they're all knots. So you can put a 1 right here. We have, and again, we have AB right here and CD right here. And these Karnaugh maps should always be given to us in this format. And if not, then you're going to reconstruct it in this way, right? So you're going to have two of the inputs on the x-axis and two of the inputs on the y-axis with every possible combination. And if you had three inputs, then it'd be two inputs on the x-axis and one input on the y-axis, along with every other combination. And then you would essentially do the same thing. So right here we have 1 for the first one, and then we have 0, 0, 0, 1. So we can do this right here. We have 0, 1, 0, 0. So that's going to be right here. We have 0, 1, 0, 1. Right here. 0, 0, or sorry, 1, 1, 0, 0. Right here. And then we have 1, 1, 1, 0. Or 1, 1, 0, 1. So right here. And again, this is going to be a very similar situation to the last Karnaugh map we saw. So it's going to look something like this. We're going to put zeros here. And again, I'm going to go ahead and circle these. Right, we got 1 of 4 and another 1 of 4. And so we're going to look at the commonalities in each group. So in the first group, we can see that we have A. We have not A. So we have not A. And then we can also see that we have not C. So not A, not C, right? And then the second group, we can see that we have, we've got B. And we have not C again. So essentially, we're going to have C and then not A plus B. This is going to be our initial expression, right? This is going to be your sum of products expression, and this is going to be simplified. And that's going to be our Karnaugh map. But let's take a look at just one more example, and I want to draw back to the example for which we actually created our expression before. So this one right here. Okay, so I've kind of transferred that expression over here, and let's put this into the Karnaugh map. So first off, we're going to have 1, 0, 1, 0. So that's going to be right here. Next, we're going to have 1, 0, 1, 1 right here. Next, we're going to have 1, 1, 0, 0. So we got this one right here, which is a bit weird. 1, 1, 0, 0, so that's going to be right here. Next, we have 1, 1, 0, 1. Next, 1, 1, 1, 0. And next, we have 1, 1, 1, 1. So we have this right here. Now remember, 2n size, right? And we need to make as few groups as possible. So I think the first one we're going to do is right here. And remember, our groups need to be either horizontal or vertical. And if we want to make another big group, we don't want another group of 2, right? So we want groups, we want as few groups as possible, and we want big groups. We want groups to be as big as possible. So we're going to end up with something like this. These are going to overlap like this, okay? So I guess the key thing here is we also want groups to be as big as possible. And really, if we only circled the top two, so these right here, we'd still have 2 groups, but it wouldn't cover, it wouldn't be as big as possible. So that's another thing to keep in mind. So we have 2 groups of 4, which is what we want. Now, if you look at this, the common, so first of all, we can see that in all of these, we have AB. And that's pretty much the only thing that's common because C and D are changing throughout this. So we're just going to have AB, we're just going to have AB plus, and that's just for that group, right? Now, if you look at this group right here, so this group right here, then we can see that A is going to be 1 for both of them. So we're going to have A, okay? And we can see that C is going to be 1 for both of them as well in this group right here. So we have AB plus AC, and that will just end up with A and B plus C as our simplified expression. So another type of, not necessarily another size of Karnaugh map, but remember, even if this Karnaugh map was smaller, then we would still do things the exact same way. Okay, now before we move on, there are a few things that I want to point out. First of all, we do need to fill in the zeros, and any questions asking you to fill in a Karnaugh map, the solution will be wrong unless you include the zeros as well. Because these zeros are essentially representing other combinations of inputs that don't exist for this particular truth table and this particular logic circuit. And in reality, these ones as well are representing different inputs. And the Karnaugh map is just giving us an opportunity to essentially summarize all of the ones that we have into a more simple solution. Another thing that I do want to point out is we do have a fairly unique set of loops in the sense they're both not squares. And so right here, we actually have a column, which is totally fine. But you might ask why we just didn't have a group of 2 and a group of 4 rather than a group of 4 and a group of 4. And the reason is that if you look back at these rules, right, the group should be as big as possible. Yes, we want fewer groups, but we also want those groups to contain as many ones as possible. And that's the reason why we did that. Anyways, we can look at more examples in the members only videos, but that about covers it, so let's move on. Okay, now in this last section of this video, we're going to be looking at more specialized logic circuits, including a half adder and a full adder. These are called a half adder and a full adder because these are used to add different numbers of one bit values. So if a half adder is essentially a logic circuit, we have 2 inputs and our outputs are going to be the sum of those binary values, of those 2 1-bit binary values, and a full adder is going to allow us to add 3 1-bit binary numbers with our 2 outputs giving us the sum of those 3 values. And for these specialized circuits, we need to be able to identify them based on the logic circuit, just based on looking at the logic circuit, and then also be able to identify and recreate their truth tables. So let's go ahead and let's get started here. Okay, so first let's take a look at the half adder. So here we have an XOR gate and we have an AND gate. And we have 2 inputs. We have an A and B input, and we have an output, and we have a sum output and a carry output. We'll talk about what the outputs are, but just analyzing this particular gate, you can see that both of our inputs are going into an XOR gate right here. And then in parallel, they're also going through an AND gate. And the output of our AND gate would be our carry output, and the output of our XOR gate would be the sum output. So that being said, let's go ahead and let's take a look at the truth table to see what's actually going on in this logic circuit. So we have our different combinations of outputs for A and B. And so what we're going to look at is our sum and carry outputs. So basically, let's take a look at this row right here, right? So we are adding the binary value 0 plus the binary value 1. And 1 is essentially going to be like 2 to the power of 0, 1. And so if we just add these, we're going to end up with 1. And so that's why for sum, we just have 1 right here. And carry, we have 0. And if sum is 1 and carry is 0, that means we're essentially representing this value right here. Okay. Similarly, sum and carry, if they're both 0, it should be that. Again, right here, we have the same value. And right here, if sum is 0 and carry is 1, we're representing this value. And the reason for that is because where we have this value, we can see our inputs for 1, or for A is 1, and for B it's also 1. So it's essentially like 2 to the power of 0 plus 2 to the power of 0. And that's going to give us 2. And the way we represent 2 in binary is going to be 1, 0. Hence why we have our carry value being 1 and our sum value being 0. The carry essentially represents 2 to the power of 1, and this one essentially represents 2 to the power of 0 when trying to represent the sum of our inputs into A and B. Now, next what I want to look at is I want to look at an example question from the specimen paper that kind of differs from the half adder. So as you can see, it's similar from the half adder, or it's similar to the half adder, but there's one nuance in that we have a NOT gate here before we get to the AND gate. So we have XOR, we have our AND, but we have this difference right here. And what we want to do is go ahead and construct a truth table. So let's go ahead and do that. And again, when constructing truth tables, we're going to start with just a group of 1s and a group of 0s. So dividing our set of rows into 1s and 0s. So we're going to have 1, 1 and 0, 0. And then always our next column is going to be alternating. So it's going to be something like we're going to do 0, 1, 0, 1. And we're going to end up with with all of the different combinations. And also although I will say to keep it consistent with the previous truth table, we're just going to start with grouping zeros. That just kind of makes it easier. It doesn't change the answer at all, but just from the perspective of comparing it to the other truth table, it makes it easier. We still grouped our zeros and ones together. So there's a couple of ways to approach this. The easiest way, actually probably the way that you should do it, is right here we see that x and y are just going to go through an XOR gate to give us a difference. So this is going to be x XOR y. Okay. If you remember anything about our XOR gate, basically when the inputs are different, we get a 1. When they're the same, we get a 0. So that means that we're going to have a 0 right here, we're going to have a 1 here, and 0 here. And then let's look at the borrow gate, right? So basically right here, we're going to have not x and y. Okay. So what I'm going to do right here is I'm going to write our not x values to make it a bit easier in a different color. So if you have not x, it's going to be the opposite of everything in the x column. Okay. So it's going to be 1, 1, 0, 0. So remember, the only time we're going to have, when we use the AND gate, the only time that we're going to have a 1 is when both values are equal to 1. So when both inputs are equal to 1. So in this case, we have 1 and 0, so we're going to have a 0. We have 1 and 1, so we're going to have a 1. We have 0 and 0, so we're going to have a 0, and we have 0 and 1, so we're going to have a 0. Now, as I said, because we have a difference output, it's generally intuitive that actually this is like a half subtractor rather than a half adder. So essentially, we're subtracting whatever the first input is. We're subtracting the second input from the first input. So like right here, if we have, for x and y, we have 0 minus 0 minus 0. And that's just going to give us 0 for the difference and 0 for the borrow. Right here we have 1 minus 0, so that our difference is just going to be 1, and our borrow is going to be 0. And here we have 1 minus 1, which just gives us 0 for both, because our answer is going to be 0. Here we have 0 minus 1, and here we have a difference of 1, but we need to borrow 1. And I'm not going to get too much into the arithmetic aspect of this, but this is essentially used to represent minus 1 in this context. Just because like if we're doing 0 minus 1, then the idea is that we're going to have to go over to the next, essentially like the next place right here. And that leads us, and we're going to have to borrow values from there. And that leads us to having a borrow right here. Like, I honestly wouldn't worry too much about this because actually in the exam, they didn't ask what the purpose of this was. But that's essentially what the circuit does, and it shows you the connection and why we actually need to learn what a half adder is. Now, lastly, let's take a look at a full adder, which essentially follows the same kind of logic. So here we have 3 inputs, and the idea is that we should be able to add all of those together. And our outputs are going to be S for sum, and then C for carry. So if you look at like some of the more complex examples right here, right? Well, first of all, what I do want to highlight is we've grouped, in column A, we've grouped zeros and ones. In column B, we've kind of alternated. So 2 zeros, 2 ones, 2 zeros, 2 ones. And then we alternated 0, 1, 0, 1, 0, 1, 0, 1, our third column. So that's an easy pattern to follow if you ever have a truth table with 3 columns. Anyways, getting back to the actual sum part of this, if you look at some of the more like, if you look at some of the more higher values right here. So for example, right here, we're adding 1 plus 1. So 2 to the power 0 plus 2 to the power 0, which equals 2. And so our answer right here is going to be a 0 and a carry of 1. Because remember, if we have a carry of 1 and a sum of 0, that essentially means this value right here. Similarly, right here, we have this larger value, okay? So we have, that's going to be like 2 to the power 0 plus 2 to the power 0 plus 2 to the power 0, because these are all 1-bit values, right? So that's going to equal 3. And 3 is represented in binary as 1, 1. Hence, right here, we just have 1 for both the sum and the carry, so we have 1, 1. And I think they didn't explicitly say it, but I think it's also worth understanding the structure, being able to recognize the full adder. So right here, we can see we have A and B going into an XOR gate, as before. But then the output of that is going into an XOR gate with C, right here. And then all A and B are going into an AND gate like they did before. And the output of XOR and C are going into another AND gate, and those are going into OR gates right here to give us our carry. Anyways, another specialized circuit worth addressing, worth being able to recognize. One thing I do want to point out as well is that a lot of chips contain these specialized logic circuits in large quantities to be able to complete these types of arithmetic operations. And that's the reason why we should learn about them and why they're probably covered on the exam. Anyways, let's move on. So the last thing we're going to do is finish off this video with some channel updates. Firstly, if you want to see additional practice questions related to these topics, go ahead and become a member. I haven't posted those videos up yet, but I will, and links will appear in the description to this video. So look out for those, and then when those pop up, then you can go ahead and sign up to become a member. Next, practice questions will be continually added as more information comes out about the exam. So those practice questions, again, will be available to members. Next, and I said this in the previous video as well, but this video as it is will be edited and re-updated after the first exam in May 2027. So I've kind of released it based on the subject guide, looking at some of the textbooks and looking at the specimen papers. But it's going to be hard to actually know what sort of nuances there are going to be on the exam until we actually see one cycle of exams. And then I will most likely edit this video and re-upload it. One last thing. I anticipate some questions as to what extent you need to be able to simplify Boolean expressions and know those like Boolean algebra laws. And I haven't seen anything but a formula sheet at all. So my assumption is you just need to know those laws and just to practice quite a bit, simplifying more complex Boolean expressions. Now, the next video is going to be the next topic in A1 for paper 1 of the exam, and that's going to be on operating systems and control systems. I hope to see you in the next video. If you like this video, please remember to like and subscribe to the channel. Have a nice day.